So here is the outline. That's the outline of what we're going to do. So I have introduced the support vector machine problem, and I have introduced Lagrangian and also the dual problem. I haven't solved anything yet. I'm just introducing that notion. And then what I'm going to do is that I'm going to really derive the dual SVM and then show you why it could be useful. All right, so this is the original problem. That's the primal problem. As what we have done before, we are writing it as the Lagrangian function. So this is the Lagrangian function. Okay, and then the Lagrangian function, I'm going to take the gradient with respect to W and also W0. So this is the primal stationarity. Primal stationarity. So if you recall, one of the 4 KKT conditions, that's the first KKT condition. So if I take the gradient of my Lagrangian with respect to W, I will get what? Well, I will get W. This W comes from the gradient of this 2 norm square of W. Okay, if you take the gradient of the square term, you will get the W. And then I take the gradient with respect to this entire sum. I will just get the sum times all these lambda j and yj and xj, because you only have one variable W here. Okay, so this is the gradient of the Lagrangian with respect to W. Similarly, you can get the gradient with respect to W0. You can get this equation. Okay, so now I have applied the primal stationarity into my problem. I got a pair of equations, equation 1 and equation 2. So I haven't got to the dual SVM yet, okay, but I have already got some very interesting observation. This equation says that my W can be written as the summation of lambda j, yj, and xj, j going from 1 to n. Okay? Now, what is this W? This W is your support vector that separated hyperplane's normal vector. This is something that you care ultimately. This W, according to this equation, it can be written as a linear combination of your data points. This is very surprising because you're writing your solution, your decision boundary, in terms of your data points. This is your data point. Okay? So what is the picture here? The picture here says that, let's say I have a group of data points, okay? And then my solution will be, this boundary, this normal vector, will be defined according to the vector specifying all these data points. Now, I want to jump ahead to tell you that this lambda j has to be either 0 or greater than 0. Where does it come from? It comes from the complementarity condition. It has to be either of the 2 cases. It cannot be negative. So if you get either 0 or positive, that means you are going to either use the data point or not use the data point, right? Because the summation says that it is y1 x1 plus y2 x2 plus ... If y1 and x1, okay, I'm using a lambda 1 here, lambda 2 here. So if lambda 1 is exactly 0, then that means you cannot out this data point. It doesn't really matter to you, okay? And then if this is positive, you're going to keep this term. If you go to the picture here, it says that I have a group of data points. This data point is hitting my my margin, and therefore I'm going to use it. Okay. Now remember that the constraint is that your yj times w transpose xj plus w0 is bigger than 1, right? So this margin is defining the distance of 1. If my lambda j is 0, that means, if lambda j is 0, that means what? Well, that means this yj times whatever has to be positive, strictly positive. And so what are the points? The points has to be living in the interior of the margin. You cannot live, you cannot hit the margin. Of course, you cannot violate the margin because it's a hard support vector machine problem. There's no tolerance. Okay. Okay. So if this is, if you get a 0, it will be right on the margin. If it's greater than 0, then that means you are in the interior. And therefore, your your decision boundary is going to be defined only by a few of these support vectors. Okay, it's not going to be defined by the rest. It's only going to be defined by these support vectors. So that is the key. Okay, so these support vectors will correspond to lambda j bigger than 0, and then your W transpose xj plus W0, and then your yj will equal to 1, right? Because they are living on the boundary, and then the Lagrange multiplier has to be positive. Okay, that's why it's called a support vector, because these will be your support vectors. Is this concept okay? All right. So let's move on and then do a little bit more calculation. So now the complementarity condition states that this lambda j times all these has to be 0. And so this is just a summary of what we have talked about. You will have either one of these two cases. Okay. You have your constraint being positive. This will be saying that your xj is in interior. Okay. And then here you have this equal to 0. This means that your xj is on your separating hyperplane H. And so then you can define a thing called the support vector set, and this set will be a set that contains all the indices j such that your lambda j has to be positive. So if you go back to the previous diagrams, this point, and this point, they will live in this support vector set, because their Lagrange multipliers are positive, or equivalently, it means that this xj is on the plane. Okay, so they're right sitting on the separating hyperplane. Now, only for those that are living in this support vector set, you are going to use them to define your support vector. Okay, so this is your weight vector. Your weight vector is going to be a summation of lambda j, yj, and xj. However, a lot of these j's, they are not in the support set. Once they're not in the support set, what are the values? There's just 0, and you can forget about them. Okay, and so this W will be defined as the summation of everyone that is living in the support set. Okay, so given this idea of this lambda, then we also want to do some simplification of my Lagrange function. Now, the following two slides would be just algebra, not very insightful, okay, but we still need to mention them. So what we are doing here is that I want to rewrite this equation, the W, all the W and W, okay, I will keep the W0, but all the W's, I want to write them in terms of this lambda j, yj, and xj. Okay, so what is it? Well, this W star will be written as the summation of lambda j, yj, and xj, j going from 1 to n. Okay, with the understanding that some of these lambdas, they are 0, and some of them, they are positive. So I want to replace the W star by all these lambdas. Okay, and then if I do that, I will have, this is the first term, I call it A. This is the second term, I call it B. In A, that's just W replaced by the sum. In B, is the same thing, that W is replaced by the sum. Okay, nothing fancy, no concept here, just linear algebra. Okay, just plug in the number. And then I'm going to do an expansion of the terms. And then if you trust me, I can show that A will equal to this double summation. B will equal to this summation with something. Okay, now you have to put a faith on me, because I did it some time ago. It could be some mistake. Okay, so you can correct me if there's any bug. But assuming that that is correct, okay, A, which is a 2-norm square of this term, can be written by this. B is the summation can be written by that. Then we can analyze these terms A and B separately. Okay. Now, There's also one more very interesting thing is that lambda j and yj that has to sum to 0. Okay, and why is that? Oh, okay. I sort of forget why this is the case, but I think that it's because all the data points, they can be correctly classified. Okay, all the data points, they can be correctly classified, and so if you are at the interior, then the lambda j's, they are originally 0, so you can ignore them. But the only thing that you need to worry about would be the lambda j's, they are positive. But then for the lambda j's that are positive, then all these yj's. Okay, so you sum. Okay, so this is the sum of all the lambda j's and yj's, and these are positive, and then these yj's, they are either +1 or -1. Then I don't see why this can go to 0. Okay, I need to check this. Okay, so this is something I need to check. Okay, but assuming that this is true, okay, I did this some time ago, I forget why, but then assuming that this is true, then what will happen is that you can sum these two up. Okay, you can sum these two up, and then you will have what? Well, you will have this 1/2 term here, and then you have -1 term here, and then if you sum them up, you will get I think there should be a minus instead of a plus. Is that true? Am I right? It should be a minus. Okay. So you have a minus here, then the problem will become this. Yes, so this is a minus. Okay, so you have a -1/2 of this gigantic term plus the summation of the lambdas, and then with a constraint that this is going to 0. Okay, so I really need to go home and think about why this is going to 0. Okay, I owe you something today. Okay, so I will find out why this is going to 0. So now, if this is going to 0, so you have this optimization problem. This optimization problem says what? This optimization problem says that you don't have any W anymore. Okay, you don't have any W anymore. Everything is written in terms of the lambdas. And this lambda is, of course, the dual variable. If I can solve this dual problem, I will be able to get a good lambda star. Okay, and once I get the lambda star, I can plug it back to the primal problem, then I will be able to solve for the support vector machine problem. Now, this problem itself is a maximum over this gigantic term, but you can also write it in terms of this matrix vector representation, meaning that you recognize this is just a quadratic optimization over the lambdas. You only have lambda I and lambda j. That's the same as just minimizing a lambda transpose q lambda. Okay, so that's a quadratic term. This is a linear term in lambda, so I write it as 1 transpose lambda. This is a linear term of your constraint, so y transpose lambda equals to 0. Yes?
That would be 0 in check your slide number 12.
Oh, slide number 12? Ah, okay. So, okay, great. Thank you. Okay, so problem solved. Okay, so I don't owe you anything now. Okay. All right. So the reason is here. Okay, this is 0 because gradient W0 of the thing is 0. Thank you. Okay. All right. So what? Well, let's go to the slide. Okay. So we have this dual optimization problem, and then this is the matrix vector form, and you want to solve this maximization problem. And then what I can do is that I don't like this form. This is not very standard. I can group the terms all together. Okay, because you also have an additional constraint of lambda being positive. And so I can group all the terms together to tell you this form. So let me skip the slide and go to the final slide, and then we go back to page 18. Okay. So what I'm doing here is that this is the ultimate dual problem that I cared about. Okay. Now let's look at this dual problem. It is a quadratic maximization problem in terms of lambda, and then with a linear term in the objective function, and then the constraint, it is just a linear inequality constraint problem. Okay. So if you compare this problem with the primal problem, let me tell you the truth that this is not much simpler. It is as difficult as before. Okay. However, we want to go into a little bit detail in terms of this Q matrix and this A matrix. Okay. Then you will see some very interesting pattern. What is the Q matrix? Well, the Q matrix, the Q is used to describe this quadratic term. Okay. And then this quadratic term here, it will have yi, yj, xi, xj. So let me just write them out carefully. Then you can see that the Q matrix is taken in this form. It's y1, y1, x1, x1, y1, yn, x1, xn, etc., etc. Okay. It's a very, very big matrix. However, it has a very interesting structure that every term contains an inner product between two data points. Okay. So now what? So now, if you really remember the kernel trick, what are we going to do? We are going to replace a term here by a kernel of x1 and x1. Okay, so then you can empower this support vector machine problem by kernel tricks. Can you do that in the primal space? No, you cannot do this in the primal space. But you can do this kernel trick in the dual space. That is a very, very powerful thing that only the dual space can allow you to do. So, when you go back to the problem here, this problem, of course, is the standard dual support vector machine problem. We are not applying any kernel trick yet, but you can see that to go from here to the kernel trick should be somewhat easy, because once I recognize the form, I can just replace all my inner products by the kernels. And then I should be able to solve the kernel SVM problem. Okay? Alright, now, solving this problem, of course, it requires some solvers, some quadratic optimization solvers. In our case, it will be CVX again. Once you have solved the solution, you will show that the W star can be written as this. What I mean? Well, the thing that you're getting out from here is the lambda star is the dual solution. The dual solution themselves, they are not useful. You need to convert the dual solution into a primal solution in order to make sense of that. Now, how do you define the primal solution? Well, the primal solution is just the summation of your lambda j star, the star coming from here, okay? Because the lambda j will tell you who are the support vectors, okay? And then now you're forming a linear combination of all these support vectors that will define your separated hyperplane normal vector, okay? And after you get the W star, you're happy, okay? Because you have solved the support vector machine problem. Okay. Now, of course, world is the world is not that simple. Okay. Are we done yet? Not quite. You still need to figure out the W0 star, but that's a lot easier. What you do is that you go to your data sets, okay, and then you pick up a x plus and x minus. They are the support vectors in your set. Okay. You should be able to find at least one of those in each part. Okay. So they are the support vectors. Now, how do you know they are the support vectors? You look at the dual variable. If they are positive, then that point is a support vector. Okay? So you pick up the x plus and x minus, and then you know that the support vector, they are living right on the decision boundary, right on the margin, and so you will have this pair of equation to be satisfied. Okay? Because x plus is on the positive margin, and then x minus is on the negative margin. They will satisfy, and so you sum them up, okay? And then you can show that W0 star will equal to this quantity. All right? Okay? Okay. So just to summarize what we have done so far, I am not making the problem easier in terms of the optimization. It is as hard as before. However, I have written it into a form that has a structure that will allow me to do the kernel trick, that will allow me to do the nonlinear transform. In addition, this dual perspective allow me to exactly quantify what do I mean by a support vector. A support vector, it is a vector, or it is a training data point that is living right on the margin. And these can be found by solving the dual problem. If the dual variable is positive, then the corresponding data point is a support vector. If the dual variable is 0, then the corresponding data point is living in the interior of the decision. Okay, so that perspective can only be drawn by looking into the dual SVM. Oh, we have a question here? Oh, okay. All right. So this is a summary. So primal problem, the thing that allows us to turn into the dual problem and claim that the dual problem solution is the solution for the primal problem is based on this fact called the strong duality, where you can turn the mean max into a max mean. Why? Well, by solving this problem, okay, you're solving this maximum problem, okay? So here is this a maximization, and then this mean is what? This mean says that I'm taking the gradient of your Lagrangian with respect to W, and then I get a solution I plug in, and then I solve a maximization outside. So this is your dual problem, because you are solving the mean first, and then you solve the max. The primal problem is that you solve the max first, and then you solve the mean. That's a different problem, okay? The two are the same because of the strong duality. Their strong duality holds because it's a quadratic programming problem. Now, this slide just summarizes how are you going to turn from the dual solution to the primal solution, which we have talked about. One is that you find a W star, and then the other one is to find a W0 star, okay? And then the W star would be a linear combination of the support vectors, and here you're just picking the two support vectors and find a particular W0. All right, so this slide just summarizes the picture again, okay? So this is what we mean by a support vector machine. Okay, now when someone asks you, why do you call this thing support vector machine? I hope you can tell them, because by solving the dual problem, you'll be able to find a set of vectors that will define the separating hyperplane, and that's why it's called the support vectors. Okay? All right. This is the reading list for this lecture. Actually, it's the reading list for the entire 3 lectures on support vector machines. You can read. I will encourage you to take a look at this chapter in the E chapter. Okay, so it's freely online. Okay, so you can find out the material. They have a whole chapter on the support vector machine. It's very, very well illustrated. All right, so otherwise I will see you guys on Wednesday. Thank you.